They find you, and now they miss you. Must I remind you?
Okay, so hopefully the fact that there are people here means that I'm in the right room, because I think I'm supposed to be talking about functional compiler design in Scala. And I've been wanting to give a talk about functional compiler design actually for quite a while. And I've been sort of skirting around the edges and talking about type theory and talking about parser theory. Now this is sort of like the big, giant ball of wax kind of big overview for those of you who want to build compilers for yourself. And you should if you don't. And you will when we're done. So why compilers? Why should we care about building compilers? After all, the Java compiler works just fine, and the Scala compiler is pretty fast, so, you know, who cares? Well, the reason, like the number one pragmatic reason to study compilers at all is compilers are the ultimate problem. And I don't just say that as a compiler enthusiast and a language designer. I mean it very literally. Compilers are the problem. So if you think about things from the perspective of computability theory, and you know, computation as a whole, right? The standard trick for talking about computation in a formal sense is to model it as a language, right? And 9 times out of 10, what you're going to do with that language is you're going to reduce it to another language that you already know how to solve, i.e. another problem that you already know how to solve. So compilers are precisely that. They're turning one language into another. They're turning one problem into another problem, a problem that you know how to solve. Well, this is exactly what we do on a daily basis. We reduce problem A into problem B because we know how to deal with problem B. So compilers are actually what every one of us does all the time. We just don't realize it because it's sort of disguised in other things. And so studying compilers gives us, at a very literal level, a lot of insight into how to solve problems in a very, very direct way. Compilers have immensely strong formal foundations. I can't remember who said this, but basically compilers are like the intersection between computer science, like formal computer science, and actual industrial practice, computer engineering. They have incredibly strong formal foundations and meta theories that go behind all of the different things that we do in compilers. There's been research into how to build compilers going back 60, 70 years. Just how to do this, how to approach these problems have been things that people have been thinking about and writing papers about and writing books about and learning more about for a very, very, very long time. And so in a sense, it's sort of fun. Like when you go in to study compilers for the first time, it's like archaeology of comp sci. It's really, really cool. So learning these things gives you a very immediate and very practical introduction to formal computer science. This is how I got into formal comp sci, and I've never looked back. Compilers are a very, very, very severe stress test for language expressiveness. It's actually very fundamentally hard to express a compiler. So this is actually one of the interesting things about many languages that are not quite Turing complete, but close. So if you look at things like System F, for example, System F is not Turing complete. It's a strongly normalizing language, which is to say that every program produces a single value, and it's always going to terminate and produce that value. System F cannot build a compiler for System F. You can't do it. It is provably impossible. See also Kurt Gödel. You can build a compiler for a language almost as powerful as System F in System F, but you can't quite do System F. And this is actually a very, very, very interesting property. So the fact that I can, in Scala, write a compiler for Scala is actually really interesting, formally speaking. I mean, we already kind of knew that Scala was Turing complete. I mean, Scala's type system is Turing complete. But, you know, the fact that we could write a compiler in it sort of is like the last nail in the coffin. We're sure now. Compilers are also among the most difficult programs to write. They're very, very, very challenging in terms of managing code complexity. They tend to have a lot of very deep algorithms that are expressed in comparatively concise ways. So this is not like your average form that's rendering some pojos into HTML. This is really hard stuff. And so when you're writing a compiler, you tend to push your language's capabilities in the area of modularity and, you know, code design and things of that nature, idioms and patterns, pretty much as far as they can possibly go. And so the notion of bootstrapping one's language into a compiler has long been considered like a high water point, a benchmark for when your language has actually arrived. I will note that Clojure still does not have a compiler written in Clojure. Just saying. And compilers are a whole lot of fun. Okay, I have been doing this for my day job for quite a while now, literally working on a compiler and building a language, and I wouldn't do anything else. It is tremendously, tremendously fun to build these things and to play with them and to sort of birth a language and bring it into existence. It's just nothing quite like it. So today we're going to talk about how you do that. All right? What are the fundamentals of a compiler? How do you build it? How do you think about it? How do you modularize it? And how do you do it specifically in Scala? Because Scala has a lot of neat tricks and tools that we can use to make this better. So compilers are broken up roughly into 3 chunks, right? 3 phases. You have lexical analysis, where you're taking the raw character data and putting it into a data structure that you can actually work with and get your head around. You have semantic analysis, which is where you define the static semantics of your language. These are things like name binding, which pretty much everyone does, type checking. You've got a lot of like static verification and other things that can go on in there, optimization, whatever. I mean, there's a lot of stuff that can fit under that umbrella. And then finally, you have cogeneration. This is actually the key thing that differentiates compilers from interpreters, right? Is the cogeneration bit. Is rather than taking our language and then running all these lexical phases and static phases and whatnot, and then just immediately running the code, we're actually like producing something that we're going to run later. And that's the distinguishing feature of a compiler. Hilariously enough, we are going to spend no time at all on code generation because it's fairly dull. It's actually the easiest part of the compiler by far, and B, Scala doesn't have anything special in the realm of code generation, right? So if you're interested in the code generation phase of a compiler, on the JVM, I recommend looking at ASM, right? Just like read ASM's documentation. That pretty much tells you everything that I could have told you. It's just like in Javadoc form and searchable. So we're going to spend pretty much all our time on lexical analysis and semantic analysis. So what is lexical analysis? Simply put, it's just taking the characters, like the raw bytes that are in the file, and bringing them into memory, right? Turning them into a data structure that we can analyze. Anyone who's ever tried to write a compiler, or at least try to start writing a compiler using a collection of regular expressions, will know how tricky this can be. Regular expressions are absolutely the wrong tool for the job, and you're not going to be able to get anything that you can get your head around just working on things at the character level, right? You have to lift it up further. And fortunately, there is a wealth of computer science research that helps us out here. Lexical analysis is the area of the compiler that is most directly tied to comp sci formalisms, and we can leverage that really, really, really directly. So generally speaking, here's our goal. All right, we've got a phrase here. This is a term, rather. It's a function dispatch, presumably. I mean, this is our fake language, so we can make it mean whatever we want. But let's say it's calling the function foo and passing the results of an expression, which is like an addition and a multiplication, right? And we have to represent this as a tree. We're not trying to evaluate it yet. We're trying to represent this in some sort of tree structure that we can look at and determine things about the code and start assigning meaning to this code. And that tree is the abstract syntax tree, or AST. And it can take on a whole bunch of different forms, but we're going to call it something like this. We have a dispatch foo node at the top, and down below it, it's got an add node. That's its only parameter. And on the left-hand side of the add node is 5, and on the right-hand side, we've got a mul and then numbers underneath that. Notice how the mul is lower than the add. This is indicative of the fact that multiplication, apparently, in our language, has precedence over addition. If it were the other way around, then the multiplication would be higher and the addition would be lower. So if you want to think about this in terms of like parenthesized terms, we are adding 5 to the results of multiplying 4 times 7, which is intuitive, right? That's the semantic we want. So clearly, like from this, we can immediately infer that parsing has to do something with disambiguation and precedence and things like that, which is what we're going to see in the next little bit. So there's basically 3 different stages to lexical analysis. There's tokenization, which is taking the input character stream and chunking it up into sort of discrete atomic fragments that the parser can look at and understand at a slightly higher level. We've got parsing, which is the real meat of things. This is where we have to sort of group things together and understand where they are contextually and build the AST nodes. And then you've got disambiguation. So this is really precedence and associativity and things of that nature in most languages, but there are also certain languages that have more complex disambiguation rules. See also Scala. Have you ever wondered why the curly brace on the next line style is so heavily discouraged? Well, try it sometime and you'll find out. Scala has some very strange disambiguation rules in its lexical analysis phase, and that all kind of falls under this umbrella. So, tokenization. All right, basically this part is the bunch of regular expressions, right? This is what I told you not to do. This is what I told you was a bad tool for the job. Well, it's actually the right tool for this job. With tokenization, what you want to do is you want to take like sets of characters, like for example, IMPORT. You want to take that and you want to turn it into import keyword. You want to take 427 space and you want to turn that into 427 number literal. Right? You're just doing like little chunks like that. You're determining string literals. You're throwing away comments. You're just basically doing all of this bitsy little cleanup work and chunking that gives the parser something a little bit bigger to work with. And that makes the parser's job a lot easier. It is very, 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 very fast to do this sort of thing. You can do it incredibly incrementally. Usually the tokenizer actually runs concurrently with the parser. Like the parser just sort of like asks for the next token, and then the tokenizer moves ahead. It's really simple. And you can encode things using the tokenizer that are sometimes very difficult or indeed impossible to encode with certain parsing tools. For example, this is a fragment of a language called Quirl. This is the query language that I work on at Precog pretty much all the time. And if you look very closely at this, even without understanding the language, you should see something a little bit bizarre. So we've got this in the middle, like the second line, there's that red path literal, okay? So this is loading the tweets.json file at the /elections path. Fairly straightforward. And this is an expression, okay? Quirl is an expression-oriented language, and so paths are expressions. Well, you'll notice down below on the third line, we've got an example of object dereference. We call .time on the tweets object. And that's a little bit weird, because we called .json on the /election/tweets thingy up above. So why is it that one of them is part of a path and the other one is dereference? Have you ever wondered about that? Like that's actually kind of weird. And most languages have examples of this sort of construct. And I mean, this is exemplified, right? So if I just put parentheses around this, you can see how it really, .json really would be a method call, except for the fact that it's right next to a path. And this is handled through greedy disambiguation. We're basically saying that, okay, once we start parsing a path, we're going to keep parsing a path until we can't parse anymore. And we're just going to keep chunking. And nothing else will possibly get in the way of that. This is greedy disambiguation. This turns out to be very, very, very easy to do in a tokenizer, very easy to do in a scanner, nearly impossible to do in a parser. So, doing this first, doing this in the tokenizer phase, makes life easier. To really drive home exactly what the tokenizer is doing, here's kind of that first line, what it looks like in tokens. So if we just sort of like scoot down, everything is chunked up, right? We've got that import keyword, the ID for std, cons keyword, time, cons star. Notice a couple of things, right? We're obviously in atomic chunks, but we're also moved up a little bit of a level from the syntax itself. So we're no longer dealing with the raw characters. We're now dealing with kind of this larger stream of chunks, larger stream of things that could fall into a number of different cases. And writing code to do this is, as you would expect, actually really easy, right? There's a number of tools that can generate this. They're easy too. You just write regular expressions. This on the screen here is part of the tokenizer that would be required to tokenize the previous slide. Basically, you just write a little deterministic finite state machine. It's really, really, really easy. And you're essentially encoding a regular expression engine directly in code. But that's okay, because regular expressions are easy. It's not that difficult to do. So, tokenizers, great. They solve a lot of problems for us. They're fast. They're easy to write. They make the parsing job easier, which is great because parsing is hard. So they've got a number of advantages to them. In general, they tend to pretty radically improve the performance of your parser. Parsing performance is actually a hilarious topic because it's one of the rare areas where theoretical researchers spend a lot of time talking about performance, and practitioners spend no time talking about it. It's like completely backwards from the rest of computer science, where normally a researcher will invent this crazy algorithm and it takes like a galactic amount of time, but they don't care because it works. Here it is like, in papers, everyone's eking out the last millisecond, which is very strange to me. So tokenizing improves parsing's performance, which is kind of fun, because rather than operating on every single individual byte, you're now operating on chunks, which could potentially represent many, many, many bytes. And so that's, it's actually an order of magnitude improvement in performance. Greedy disambiguation, which we already talked about, right? And users actually tend to expect this semantic. I'm not really sure why. Personally, I don't expect it, but in general, people like looking at languages and reading tokens greedily from left to right. So, okay, tokenizing does that for you. But there's a lot of disadvantages to scanning, to having a separate tokenizer. It introduces some complexity, right? You have another layer. Layers are bad, bad for complexity. They introduce abstraction, but they also introduce complexity. So you've got to manage your separate thing that's running at the same time as your parser. You've got to manage your separate tool that generates your lexer as well as the thing that generates your parser. They have to talk to each other. It can be a little bit dicey to get that whole dance right, especially if your build tool is something that doesn't already natively know about them, which is generally the case. So there's some problems there. You also have problems with irregular constructs. Now, what do I mean by irregular? Well, it's not just a euphemism for weird. Irregularity is something that actually has a very specific definition. It means a construct that cannot be encoded in a regular expression. So the classical example is parentheses, right? You can't do parentheses matching in a regular expression. Well, it turns out that something very much like parentheses is comments. How many people have done something like this at least once in your career? Yeah. So we tried to wrap a block of code in a comment block, and we didn't realize that there was a comment block in that block that totally negated all of the effort. And fortunately in C, */ is not actually a valid token in real code, but there are some languages where it is, and that can really throw you off. So yeah, this sort of thing is actually pretty common. Most languages suffer from this. Here's another example from Ruby. We open up a string literal, terminated by something, certainly not quotes, and we don't really know what that is. And somehow the tokenizer, which is determining what is and is not a string, has to be able to handle this. My favorite example of all, Scala, XML literals. Here, we're sort of going along, and we're treating tokens like Scala would, and the less than and the greater than operator, those are actually operators, and they become method calls, blah, 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 blah. And then suddenly we hit an XML literal, and now we're in weirdo land, because everything else behaves differently, and text needs to be tokenized as text. And then, oh, we hit a curly brace, now we're back in Scala. Close curly brace, back in XML. And it's weird. It's very, very, very strange, and it's very difficult, and in fact, provably impossible for a lexer to be able to chew through this, to be able to understand what's going on here. So the solution that Scala takes is to go without a lexer. Hilariously, Ruby actually does have a tokenizer. I apologize, I'm going to be using the words tokenizer and lexer and scanner completely interchangeably. They're all synonyms. So Ruby actually does have a separate tokenizer and parser, and they sort of like have this unholy communication between each other where the tokenizer goes along and feeds things to the parser, and the parser says, wait, stop, backtrack, do something different, I just saw something that's weird, and then the tokenizer does something totally different over here, and then the parser like tells it to go back. It's very weird. I don't recommend ever building a language like that ever again in the history of the world. Just do it without a scanner. It's much, much, much easier. It's what Scala did, and we know how well that turned out. So scannerless parsing is parsing without a scanner, which is pretty much what you would expect from the name. What you do is you have the parser operate directly on the input stream. It's actually reading the bytes directly. No scanner in between. And this has some advantages, right? It gives the parser a lot more control about how it's interpreted. It allows you to define the lexical syntax of your language in one place. So you have a single specification, the parser, which knows what string literals look like. It has a regular expression for them. It knows what integer literals look like. And it knows how ifs and thens and elses and pluses and minuses all kind of compose together and disambiguate. Speaking of disambiguation, scannerless parsing has a problem, which is that it introduces some ambiguities, and we have to have a way to deal with them. And I'll get to that in a little bit. So first, we've got some Scala code that doesn't involve XML. Yay. This is an example of a scannerless parser written using GLL combinators, which is my parsing framework. The syntax is conceptually very similar to what you would see with Scala's parser combinators. So you can sort of like switch the bits in your mind, and it almost becomes the same thing. Basically, what we're doing here is we're defining a tiny little trivial expression language that can have integer literals in it or negated integer literals. Very complex. So you'll notice we've got a minus sign written directly in the grammar, right? We're dealing with tokens and we're dealing with characters directly. We have a regular expression just plopped into the grammar, exactly where you would expect it. So it's kind of nice. It's very easy to manage. But there are some complexities, as I said, some ambiguities that get introduced. So here's a slightly more complex expression language where we can accept null, integer literals, and identifiers. Okay, the identifiers are kind of useless because they don't mean anything, but we're going to accept them anyway because we're parsing. And you'll notice something's a little bit fishy here because this null token, right, NULL, happens to also be matched by this regular expression. So who's to say whether or not NULL is in fact the null keyword, or is it an identifier of some sort? And answering this question is actually fairly tricky. Some languages do things like they'll parse null or this or false as an identifier, and then they'll have like a special, if then else that checks, is identifier name equal to null? Kick it out, is this equal to null? Kick it out, like etc. That sort of thing, right? But that's extremely non-declarative. Parsing specifications, grammars, are supposed to be declarative formal models that we can reason about and understand. And yeah, that's not cutting the mustard. So this is a little bit of a problem. And what you generally have to do to solve this is introduce something called a negation class. It's similar to a negation class in regular expressions, which is like the caret inside the square brackets. Basically, we're saying that, okay, identifier, you are allowed to parse anything that is an identifier, unless it also happens to parse as a null, in which case, reject it. And this is something that GLL combinators has support for, and SGLR, which I'll talk about in a second, also has support for, but basically nothing else does. It's not a very common feature to have. Here's a slightly less trivial grammar. This is actually drawn directly from the curl grammar in our compiler. And here you can see actually the ambiguity I talked about earlier with dref and path literals very directly in the grammar. So here's the dref operator right here, dot. All right? On the left-hand side, we have an expr. On the right-hand side, we have a property name. And we turn that into descent, which is code for dref, because I was tired when I wrote this. And down at the bottom, you see a regular expression. And in the middle of this big, long gobbledygook, we have dot. All right? Dot is clearly a valid character inside of path literals. And so between these 2 points, we're actually going to have an ambiguity. And GLL combinators is going to detect that, and it's going to say, well, you didn't tell me what you meant. I'm going to give you both possibilities, which is pretty much never what we wanted. So what we have to do is actually shown on the screen. It's this preferred combinator. Okay? This is basically saying that whenever we see a path literal in a disjunction, we are going to ignore everything else in the disjunction. All other possibilities fall off the table until we have taken care of the path literal. And we'll parse as much of that as we can until we can't go any further, and then we'll look at other possibilities. So it's basically encoding very explicitly the fact that we want path literal disambiguation to be greedy, to be extremely greedy. And yeah, so that's what we wanted. That's the semantic we wanted, but we had to actually tell GLL about that because GLL is doing exactly what we say. It's not hiding some sort of disambiguation in the structure of the parser. So what tools do we have available to do this, specifically in Scala? Well, we have parser combinators, which I've already talked about. We have a number of different tools that provide peg parsing, which stands for parsing expression grammar. And do not let the name fool you. What you use is not a grammar, at least not in the context-free sense. Parsing expression grammars are really fun because they automatically disambiguate based on the first thing you wrote, right? So in the example where I had null and then an identifier below it in the disjunction, null would always win, every time, no problem. And that's just because we put it first. Well, that's actually a little bit strange and not at all what context-free grammars do. It may be intuitive, but it's not formally correct. And it yields certain situations that you can contrive with pegs that look like grammars. They look just like context-free grammars, but they're not. And they parse some language, who knows what, and it's very, very confusing to debug sometimes. Very, very, very subtle what you have to do with them. Pegs are also exponential time in the worst case, so got to watch out for that. Packrat parsing is an improvement on this. This is what Scala's parser combinators have done since Scala 2.8. Packrat parsing is basically peg with memoization, and it's very clever. It reduces the worst case bounds to n squared, which is nice, right, where n is the length of the input. But they still have the first match problem, except they complicate it slightly by making it not always first match. And it's not really clear when it's not and when it is. And you're sort of staring at your grammar that happens to have a left recursion way down here that throws off this up here. And like, who knows what's going to happen? So Packrat parsing and peg parsing, deceptively convenient, very, very dangerous. But you know, they're there. And you know, if you've got something simple to parse, they're great. Like, you have them and use them, and by all means. GLL combinators, which is my project. GLL combinators is really nice because it parses everything. It handles any context-free grammar. It's not a parser combinator framework in the sense that it has like first match or anything like that. It's actually handles the full breadth of context-free grammars, but it gives you ambiguities, right? So if you have a grammar that's ambiguous, GLL won't help you. It's just going to give you all possibilities, and you have to figure out what's going on. So that can be confusing sometimes. It's also a little bit slow at the present time due to constant factors. The worst case is really good, but the constant factors are quite bad. So not quite ready for production use, but cool. Really, the best of the lot here is SGLR, which is a project that was Ilko Visser's dissertation, actually. And it's part of the ASF plus SDF project that you can Google that and you'll find it. SGLR was really the first scannerless generalized parser. It was kind of bringing those two worlds together. And they really did a huge amount of research in encoding practical grammars in a scannerless setting, and all of the ambiguities that you run into and the best way of dealing with them. So the concept of negation classes, yeah, they came up with that. The concept of disambiguation filters, they invented that too. So there's a lot of fun things that they came up with, and they really are the originators of this whole subfield. So if you want to go straight to the source, SGLR is it, and they compile down to Java code. So you can use them pretty directly. So how does this actually render in Scala, right? How does the code actually look? Well, the first thing we need to do is establish an algebraic data type for our AST. And what we're going to do is we're going to put this inside an AST trait, because we're going to use the cake pattern because we're awesome. And inside of this AST trait, we're going to have an expr. And then there's actually a sub-object inside of here in which we hide the AST cases, lambda, application, and variable. We do this so that we don't pollute our namespace. Random cake trick. It's actually very easy with large cakes to get extreme name collision all over the place and have a really hard time separating it. So having sub-objects like this puts you in danger of race conditions, but it solves the problem, which is kind of fun. So we live dangerously, and we put it inside a sub-object, and that's where our algebraic data type lives. Inside of the parser trait, which inherits from AST, we are also going to inherit regex parsers, which is a trait that GLL combinators provides us, and basically gives us the magic stuff. And with the magic stuff, we use this little DSL and express what looks like a context-free grammar. Okay? Anything that has a lambda followed by an identifier, followed by a dot, followed by an expression must be a lambda. Yay! And we parse it as such. Expression followed by expression, that's an application. We've got parentheses and identifiers and all sorts of other fun things. And it all pretty much works the way you would expect. The only thing we're missing is a way to deal with GLL's funkiness regarding ambiguities. Because remember, if there's some sort of ambiguity in the grammar, and it turns out there actually is, cookie for anyone who finds it, the GLL will give us all possibilities, right? So we have to have a way to deal with that. We also have to have a way to deal with the fact that GLL will not give us just one parse error. It will give us like a bazillion parse errors because it doesn't know which one is the right one. So we have to handle that using a function like this. So this parses a string and collects a whole bunch of successes from the results. And if any successes exist, use the first one, because that's got to be the right thing to do. And if no successes exist, then we'll just gather up the failures and filter them somehow and maybe throw an exception. I don't know. So we'll do something there. That's like left as an exercise to the reader. But this is basically how you would do a scannerless parser conveniently in Scala. This is the sort of code that I work on a daily basis. But as I said at the beginning of the talk, it's not all there is to a compiler. I love parsing, so I could spend like hours talking about this stuff. But we don't have that long. We have to move on to semantic analysis. So semantic analysis is where you define the meaning of your language. Okay? So in lexical analysis, we define how your language looks to the user, to the actual characters they have to type in a left to right fashion. What do they have to do in order to communicate with your compiler? The parser defines that. Well, now that they've communicated with the compiler, you have to define in static analysis what that communication means. All right? What does it mean when a user tells me public static void main string, whatever it is? So we do that in a number of different steps. Okay? Usually name binding happens pretty early because name binding is important. Type checking. We love static typing, so we're going to do that too. And usually, if you're in an object-oriented language, one of the interesting things about object orientation is that name binding is actually tied to the type checker, so you kind of have to do them all at once. If we were in a functional language, we could separate them, and that would be fun and much easier to organize. But you know, just something to be aware of. Optimization, very, very important. Wish Scala did more of it. Optimization is like looking at code and seeing that this thing and this thing are sort of connected, and maybe we can inline them together, and you know, maybe this closure can be eliminated like this because it never escapes its scope. Like, there's a lot of fun things you can do like that, but it is immensely complicated. There are like whole books devoted just to static optimization of like method calls. One tiny little subfield. So static optimization is like a huge area of research and very, very much ongoing and not easy at all, but fun. And all of it would happen in semantic analysis. There's also simplification, which arguably falls under optimization in some sense, but this would be things like tree shaking and dead code elimination, right? Not really optimization in the traditional sense, but you know, doing things with the AST that's changing stuff around. So speaking of the AST, that is going to be our hammer with which we will hit our toe and do things in the semantic analysis. And we're going to have three different ways that we can do this. Three different techniques that we can use to express the rules of semantic analysis. And trick number one is AST rewriting. Okay? We've got a tree. We know how to deal with trees. Let's take this tree and turn it into another tree. We can do that. That's a rewrite. And we can express some more information in that. So this would be like, while we traverse down the tree and we're trying to determine, you know, which var node connects to which lambda node, because this var x is actually meaning this x up here. So we want to connect them together, so we go and rewrite this var node to actually point to this lambda node. That would be a tree rewrite. Another thing we could do is attribute the tree. And an attribute, this is this notion that every single AST node has some data associated with it, okay? And in an object-oriented language, we store that data in fields, usually. So there's some fields at every single AST node that has some data that tells us things about the node. So the var node, for example, the var node might contain a pointer to its lambda. And so we can find out where this variable came from. We also have the idea that we could compute lookup tables. Okay? This is kind of an indirect notion of attributes, but basically it's like, well, every single AST node has some map, you know, some entry in some map somewhere that gives us some associated data. So rather than it actually being fields on the object, it's entries in a map. That sort of works. And we're going to explore kind of what all of these things mean. But before we do that, we have to get a very, very, very important factoid out of the way, right? Factoid. The AST is not a tree. It is a graph. This is a huge misunderstanding. The AST, very understandably, people think that abstract syntax tree would be a tree. It's not a tree. It's a graph. The reason it is a graph is because you have nodes that are lower down in the tree that can point to nodes that are higher up, or siblings in the tree. And you can't represent that as a tree anymore, right? So here's an example. Here's a bit of ML code, right, which would be like the 6th language that I put on a slide. So in this ML code, we've got a let node that defines some variable x, which is equal to 4, and then we use that variable, x plus 1. Done. Awesome. So what does the AST for this look like? Well, it's got a let node at the top, and then on one side it's got a binding for x, and on the other side we use it inside an add node. Very, very, very straightforward. But what happens when we take this var x node and connect it to its binding? Well, we get a nasty little arrow completely running counter to the flow of our tree. And try as you might, there is absolutely no way you can represent this as a tree. There's just no hope at all. Because the arrows are all sort of running in contradictory directions, and you're going to end up with a node that has more than one parent, specifically var x. Or bind x, depending on how you look at it. So this is a big problem. And it sort of actually raises the question, well, what is AST to begin with? Like, is this data structure a lie? Do we have to get something else? Does our parser have to produce something different? Well, no. The AST is a spanning tree on the underlying graph. What a spanning tree is it's basically a tree, right, that contains all of the nodes that are in a particular graph, and some of the edges, all right, some of the arrows connecting those nodes, such that the structure is a tree. Well, that's what the AST is. It's a lexically derived spanning tree on the underlying semantic graph. Now that we are in the semantic analysis stage, we're playing with the big boys, and we have to have the underlying graph. We have to view this as a graph. And this immediately kicks out tree rewriting. We can't do rewrites on an abstract syntax graph. It just doesn't work, right? Rewriting a tree, easy. Rewriting a graph, next to impossible. Rewriting a graph where the edges are a function of some context around them, like what let node you're inside, and maybe you rewrote that, right? That's categorically impossible. Like, you just can't do that. So it really is not going to happen. So we had a couple other options on the table. Remember, we had attributing the AST, where we're putting like fields on the AST nodes and making them point to other things, and we had pointers and whatnot. I don't know, that sounds very C-like, so we're not going to do that. Let's try the lookup tables idea. So here's a implementation of a name binder for our lambda calculus, okay? So we have a function that's very small on the screen, but hopefully legible. It takes an expression, which is a tree, a spanning tree, remember, and some environment context that says, for this name, you actually want to point to this lambda, and returns a map from variable to lambda. Right? So it returns the associations between the variables and the lambdas. And we just sort of like happily traverse down the tree and put things into our environment and take them out again. And then we hit a variable node and we look ourselves up and we hope that we're in there, because that's when we return a map. And if we're not in there, then we're in trouble. Presumably we should report errors to the user somehow. But that's where things start to get messy. I mean, we don't want to throw an exception, because exceptions are bad. And they would stop the whole compiler, which is not what we want. Presumably, we would have to return like a pair of set of errors and map that contains our data. I don't know. It's getting really, really, really ugly. And we also have the problem that, these variable nodes, right? These variable nodes just contain a string identifier. So we've got a var x over here in the code and a var x over here in the code that are totally unrelated, but guess what? They point to the same thing in the map. So this is a little bit annoying, and we have to do something with object identity to be able to solve this. So lookup maps are a very intuitive solution. As functional programmers, we look at things and we're like, how can I put a data structure on top of that? That's just what we do. And so we see this, and we see functional maps. We can build up this map in a compositional manner, and that's great, and everything is immutable. But we start running into problems. We require synthetic keys. The standard solution to this is to have some sort of key source that just increments an integer, right? And you sort of carry this along as state, and you just keep assigning new identities to nodes, and it's a very synthetic and annoying thing. A lot of compilers in ML actually represent the AST as like every single node is a pair of integer and node data. It's very clumsy and very annoying. Speaking of clumsy, the lookup tables are very clumsy. They're very difficult to work with. Think about it. Once you get this result from your name binder, you have to carry that with you for the rest of the compiler. And the name binder is the simplest phase. Like, type checking is usually a beast, depending on how complex your type system is. And, static analysis and whatnot. You've got to take this map that you just computed and pass it as a parameter to all of those phases. It's really, really annoying. Or, maybe you could just sort of glom everything into one map and just do everything all together, and that starts to run very afoul of type safety, and it'd just be really, really weird. You end up with one of these lookup maps for every single phase. So the namer returns a lookup map, and the type checker returns at least one lookup map, and you've got lookup maps over here, and if you have 10 phases, you're taking all 10 maps and passing them as 10 separate parameters to your code generator. And that's bad. So let's not do that, all right? Let's really not go there. It's horrible. This kind of leads us back to just option 2, remember? Which was attribute the AST, right? Put fields on our AST nodes. That can get a little bit complicated. So the solution to the problems that I have not yet explained, because I'm that organized, is the atom. Okay? This is atom not in the Clojure sense, not in the Akka sense, but in the I ran out of names sense. So what we really need here is a non-local lazy val. All right? We need a field on our var node, for example, that knows how to connect itself to the lambda node. But remember, the lambda node is sort of above it in the tree, so we can't just use a lazy val because that could only look at things that are underneath the var. So we have to connect them up in some very strange ways, and we kind of want a lazy val, but not quite. Another way to look at this conceptually would be, well, we could have a write once variable. Okay? We could have a variable that you can write into that takes on a value, but that value never again changes. So it's almost like a lazy val, but not quite, sort of approaching that. The notion is that if you take this concept of a write once variable, okay, and combine it together with the ability to populate itself, okay? So a write once variable that when you ask it for its value, if it doesn't already have it, it can go off and call some other function that will at some point write into this variable, right? If you combine these together, you get something that is externally pure. Externally pure. So you can never observe that the value is changing because you never see it being anything other than what it is. Under the surface, you know that it's kind of sneaky and mutable, but in reality, it's not actually happening. And this was very definitely inspired by John Boylan's paper on remote attributes and attribute grammars. It's a really cool paper. He has a lot of neat ideas in there and goes into a lot of the stuff that inspires this. But basically, this provides us with a way of putting data onto the AST after we've created it without using var. Okay? So we can add data to our AST. We can put data on the AST nodes as fields without using things that appear to be mutable. So we don't have to break our functional contracts. And that's pretty neat. So the implementation kind of clears things up a little bit, I think. So this is, we're going to start working our way through Atom. And it basically contains a var value. Remember, it's mutable under the surface. So we have a value, and we have 2 flags, whether or not it's set, whether or not it's forced. And by the way, you should be immediately thinking of concurrency when you look at this, whenever you see non-volatile vars. That is absolutely true. And in the actual precog codebase, which has this class is this giant, ridiculous state machine doom of locks and unlocks and swapping this over here. And it's very, very complicated, and I don't recommend people write this for themselves. But it does the job. And this is kind of the assuming single-threaded model version of that class. So we have a value, we have 2 flags, set and forced, and we have a function that can populate us. And by default, that just throws an exception because that's what we do. And this populate function, presumably we're going to override it to do something sane and actually put a value in here and set the set flag to true. We have an update function. Okay, this update function looks at the set flag, looks at the forced flag, and actually sets a value. Once it sets the value, it sets the set flag to true. Notice it doesn't set the forced flag to true. So what is interesting about this is you can set an atom as many times as you want. You can keep on changing that value as much as you want, as long as no one ever looks at it. As long as no one observes the fact that you are doing heinous things, you can keep on doing them. And it's not until someone actually picks out that value that you have to stop changing it. And if you preserve this, you will still have something that is externally immutable and pure, which is kind of cool. We have an apply method. Okay, the apply method is how you get things out of Atom. So the apply method immediately sets the forced flag. So we're looking at the atom right now. We have to stop changing it, hold everything. And if we're already set, then we return the value and we're done. If we're not set, we self-populate. And if we're still not set after population, something horrifying went wrong. And ideally, we would end the world, which is kind of what an exception does. So, I don't know what else we can do there. So we just die. And after that, we return a value because we're already dead, and that's okay. A couple of different factories that allow us to create these atoms pretty easily. So this is just a way of creating one that has its ability to populate itself, as well as a function that can create one that can't populate itself, which is a bad function to use. Never use that function. So how do we actually use Atom? Because that's the really interesting thing, right? Does this actually enable us to write compilers more easily in a more clear functional style? Well, let's see. The first thing we have to do is define a set of phases. Okay? We build this in an abstract sense. So we have a phases trait that will contain all of the different phases that our compiler has. Name binding and type checking and various static optimization phases. Whatever we want to do, we're just going to throw it in here in abstract form. And we have some data associated with these phases, in this case a binding, that we're going to define as an abstract type, so that the name binder can do whatever it wants with that, and we don't have to worry about specific implementations until later. Once we've got that, we can modify our AST. Okay, we're going to change our AST structure a little bit, and on our var node, we're going to add a binding attribute. Okay, so we're going to add a binding that reads some data out of our atom using the apply method and returns it. This data is presumably of type binding. And then there's some internal stuff that we hide from the world that deals with the atom. So you notice if you're looking at this from the outside, okay, so if someone just parses some code and gives you an AST, an instance of expr, you could go down and you could find your vars and you could call the binding method and you would get a single value. And because of the semantics for Atom, you would always get the same value. So from your perspective, this is just a field that was on the node when it came out of the parser. And only the name binder needs to know any different. The name binder needs to understand how to put these things together. And that's what happens down in the atom definition. So down at the bottom, we have underscore binding, and then we've set up this atom with a function that self-populates it. The function that populates it is bind names. And you notice this is a little bit weird. We're actually calling bind names on this. This is wrong. We're going to have to fix this, but we'll come back to it in a second. So the binder, what does the binder do? Well, the binder is the bind names function that we defined in abstract form earlier. It takes an expression and then starts doing this recursive traversal on that tree. Okay? So it just walks down, recursively walks down the tree, finds lambda nodes, puts them in the environment, and then finally finds a variable node. And as soon as it finds a variable node, it just sticks it in the binding. Right? It uses that binding equals function, the mutator, and just shamelessly mutates the tree. But it's okay, because no one's looked at it yet. Right? We can keep mutating things all we want, because it hasn't yet been exposed. We mutate onto the binding. If we don't have a binding in scope, we just give it a null binding, and then we're done. Right? We just keep walking around the tree, and we set up all of these pointers. And everything just sort of falls into place. But I said earlier that there's something tricky about the bind names thing, right? Bind names can't actually be called on the var node because the var node doesn't know about the lambda node that it needs to be connected to. What we really need to do is call bind names on the entire tree, on the entire AST. We need to give that, the root of the tree, as a parameter to this bind names function so it can go through and do everything all at once. And the way we do that is currently extremely ugly. It's this thing up here, this atom. This is terrible because remember I said atoms that can't self-populate themselves are really, really bad, because remember what they do is they throw an exception. And then it turns out that if you catch that exception, they'll throw another one because you didn't set the value. So, you know, atoms that can't self-populate aren't pure. They're mutable. They're basically just fancy variables. So this is really bad, right? It solves the problem because we can have a function that, given an AST, goes through and sets all of the root values on every single node, right? And configures these pointers to point back to the top of the tree. But it's really, really terrible, and we don't want to do that. The solution to this is something that I actually haven't coded up because it's complicated, and it's very difficult to make it work. But basically what you want to do is you want to have every AST node take like a lazy expression with it that points back to the top of the tree, which hasn't been created yet. So you have to use a little bit of like lazy trickery in your parser as you're building this AST. I can show you guys what that looks like. If you're interested, you can come up to me later and I can kind of give you an example of it. But I didn't put it up here because, like I said, I haven't quite gotten it working yet. It's very tricky, very, very complex, but potentially can solve this problem in a way that doesn't require a non-populating atom. So we are rapidly approaching our wall of time here. So I'm going to move things on to the conclusion. Tree walking. Tree walking is basically the you know, what we do in compilers, right? We're just dealing with this spanning tree on the underlying graph. The AST is a graph. We're manipulating it through a spanning tree, and we're just walking around and we're looking for connections between this thing and this thing and this thing and this whole subtree over here, and these things kind of mean this thing over here, like what we did with the name binder, where we said, aha, this variable node is connected to this lambda node. They're kind of, you know, they go together. Atom. Atom is kind of the magic sauce that holds together the semantic analysis layer. This is proven to be a really neat tool in practice. It allows us to do things like we would with a lazy val, but without the limitation that everything has to be a subtree, right? Without the limitation that everything has to happen sort of individually. And this lazy val populates by itself, and this one, they can all populate together. And they are externally pure. As long as they know how to self-populate, you will never be able to observe them in a bad or inconsistent state. And like I said at the top and wave my hands vigorously, code generation, usually not very interesting because it's just sort of like walking the tree again, which we've been doing a lot of during the semantic analysis phase, and just emitting bytecode or emitting Java or JavaScript or whatever else we want to emit. Like by this point, we're really familiar with what the AST means and we can manipulate it and just do stuff. So that's all the material I have. Does anybody have any questions? So the comment was challenging my assertion that code generation is a trivial step, and makes the point that some compilers actually generate things called a control flow graph, confusingly abbreviated CFG, which is the same thing we use in a parser. And you walk that control flow graph, and you can prune things and do stuff with that, and then sort of emit from there. Yes, that is true. The Scala compiler actually does that, which is kind of interesting. And the precog curl compiler sort of does that, but not quite. That is a valid point, I think. Generating a control flow graph is sometimes interesting, but it's tricky because you can't always do that in a way that's directly natural. And so I think a lot of compilers, at least a lot of the compilers that I've worked on that do code gen, tend to do stuff from the AST directly. And there's actually a movement afoot. I think there's actually even a branch on GitHub that takes the Scala compiler and changes it so it no longer does the control flow graph. So I think that would actually be something that would be interesting to talk about. It's certainly not as trivial as I sort of glibly represented, but we really did not have the time for it. Yes?
Is your trickery related to the fact that some attributes basically go down the tree and other ones kind of go up, and that you cannot really deal with it, like for example in Ast you could do with a letrec, or can you deal with it
So the question was, if I can paraphrase a little bit, does the trickery stem from the fact that some attributes move down and some attributes move up? And is this just because it's not? Do we have to do this because it's not quite efficient enough to do things with like lazy recursion and things like that? That's a really good question. So theoretically, if we could make the root node, the root pointer, bind itself lazily through the parse process, like I was talking about, then yes, you could do it all with lazy values. But then you would be rerunning your name binder for every single variable node in the graph. Every single variable node would re-trigger the name binder and would have to go over the entire tree again. That would be pathologically inefficient, especially with some phases that are, perhaps not as efficient as the name binder, which is linear time. The other question was sort of related to attributes moving up and down. And some attributes come from below you in the tree, some attributes come from above you. This is a very important distinction to keep in mind. Attribute grammars would call this called the attributes that come from below synthetic attributes, and the attributes that come from above inherited attributes. And synthetic attributes are very easily handled with lazy values. Inherited attributes are not. And that is really what sort of triggered me to go and look into Atom. So at this time, I apologize, we're out of time, but if you have any other questions, come see me.